Hi everyone. So today we'll be looking at mathematical induction, which have to do quantities. So this example here, given that the 3 to the power n is greater or equal to 2n plus 1. So what prove by induction that the left-hand side is greater than that side. Okay. So we know that the first thing that we need to do is the first step where we have to test any positive data. One. So this is our S1 step, or the best step. We say S1. So prove for n equals to 1. So from the n is equals to 1, we're going to replace n on both sides. So on the left hand side, we have 3 to the power 1. And on the right hand side, we have this should be greater or equals to 2. Then put 1 there, we just replace n with 1 plus 1. So this will be 3. It's greater or equal to 2 plus 1. 3 greater or equal to 3. So this is true. This is true for n equals to 1, because we know that 3 is greater or equals to 3. Okay. So now we'll move on to the inductive assumption, or the hypothesis part, where we make an assumption to say just replacing the value of n with k. So the inductive assumption, so sk, which I'll just call inductive assumption. Okay. So in the inductive assumption, we're just going to replace 3 power k is greater or equals to 2k plus 1. Now, since it's an assumption, we're saying that for all n member of positive integers. Okay. So since we're using k, it's the same thing. So the inductive assumption, this is where we say we replace n k. My inductive assumption. So I'll go to step number 3, which is the k plus 1 step. So prove that it's true for k plus 1. So once we prove that it's true for k plus 1, then we have proven that this is true by mathematical induction. Okay. So we're going to pick one side, which is the left hand side, to make it look like the right hand side. So first of all, we're going to say let n be equals to k plus 1. That's our step that we're looking at now. So we have 3 to the power k plus 1. We're replacing n with k plus 1. This should be greater or equals to 2 bracket k plus 1 plus 1. So let's replace n k plus 1. Okay. So now what we're going to do next is we're going to expand the left hand side so to make it like the right hand side. Okay. So let's work on the left hand side. So left hand side, what we have is 3 to the power k plus 1. Now, since the powers are adding, it means that the bases were multiplying. Of course, now if the bases are the same and the two indices are multiplying, simply add exponents. So this came from the fact that this is the same as 3 to the power k multiplied by 3, sorry, so this will be equals to 3 to the power k multiplied by 3 to the power 1. So since the bases are the same, add the powers, we get back to that. Now, according to the assumption, you know that this like 3 to the power k is greater than this 1. So what I want to do is we're going to say since 3k is greater than this, then this means that whatever expression that we're written here is greater or equals to. So since it's greater than 3 to the k, then it's obviously greater than, so that would 2k plus 1 and 3, let's say that. So what has happened here is we've been told that 3 to the k is greater or equal to this. So it is greater or equal to this, meaning that since it is greater or equal to this, then it's as good as saying here where there's 3k, you can say this expression with 3k is greater or equals to this expression, is like what we have on the right hand side. Okay. So now from there we can do our expansion, of which our expansion in this case would be 3 times k. We're going to get 3 multiplied by k. Sorry, let me write that again. So what we have here will be 3 times 2k, like that. Then 3 times 1, so that is 3 times 2k, we get this. Then 3 times 1, of course, we just get 3, like that. Now, let me just write this. So we are here, we have 3 multiplied by 2k plus 3. Now, this statement, if you remember very well, this statement must be greater than this. So why is it greater than this? Simply because we have the 2k here. So this statement, we're going to say this whole statement is greater than 2k plus 3. So the whole statement is just greater than 2k plus 3. So the reason why we are making the reason why we're saying this is simply because this is being multiplied by 3. So of course we get 6k plus 3. But this is just 2k plus 3. So this 3 that we have here, it's as good as having a 1 that we want right here. So we have the 1 here. Then we can simply say this is greater than this. Now the question is, why are we doing this? We're doing this so that we try to produce, or to reproduce rather, what we have on the right hand side, which is this part here. So that if we say 2 times k, we get 2k. 2 times 1, that would be 3. So what we have here now, what we have at this stage is this whole statement that we have is just equals to 2k, like that, plus 2 plus 1, because 3 can be written as 2 plus 1. So that this is equals to, factor out a 2 here, so that we have 2, open bracket, k plus 1 plus 1. Then you see that this gives us the right hand side, this part here. So this is greater than this, this is equals to this, this is equals to this is greater than this is equals to this, then this of course is just equals to this. Meaning that what we have at this stage of the left hand side is greater than what we have the final step. Meaning that this proves by induction that the left hand side is greater or equal to the right hand side. So we can even give a conclusion and say this is true. This is true by the principle of mathematical induction. Okay, so let's look at another example. So in this example, we want to prove that n factorial is greater than 2 to the power n for all numbers that are greater or equal to 4. So let's proceed with the first step. So in our first step, since n is supposed to be greater or equal to 4, so we can't use 1. We want to use 4 instead. Using use 5 as well. It's just okay. So we're going to say in our first step, we call our S1, but in this case, as we're using 4, so we're going to call our S4. So we're going to prove for n is equal to 4. So you can use 4, you can use 5, anything greater than 4, because we're saying greater or equal to. So let's prove for 4. So if we put a 4 there, we have 4 factorial is greater than 2 to the power 4. So 4 factorial, 4 factorial is the same as 4 times 3 times 2 times 1 should be greater than 2 to the power 4, both are 16. So 4 times 3 times 2 times 1 should give us 24 greater than 16. So this is true, 24 is greater than 16. So we even give simple conclusion that this is true. This is true for n equals to 4. Then we move on to the inductive assumption. So the inductive assumption, we're going to say, so this is our SK, inductive assumption. So in the inductive assumption, we're just going to replace n, k. So the inductive assumption is where we say let n be equal to k. So that where this n, we're going to have k factorial should be greater than 2 to the power k. Now, this should be the same. It's an assumption. So this we're just making an assumption. We're going to say for some arbitrary number which is k should be greater or equal to 4. So for k being greater or equals to 4, simply because we're replacing kn with that. Okay, so we can move on from there. So now we're done with this step. We're going to go in the final step. So in the final step now, this is when we prove for k plus 1. So sk plus 1. So this is the parts that we need to follow through carefully. Okay, so from the original question, we're going to replace n with k plus 1. So that what we're going to have will be k plus 1 factorial is greater than 2 to the power k plus 1. What we have. So from that step now, we're going to break it down. We know that the factorial is given by 5 times 4 times 3 times 2 times 1, meaning that k plus 1 factorial is the same as k plus 1 factorial equals to k plus 1 multiplied by k multiplied by k minus 1 multiplied by k minus 2, just like that. So we're just going to break it down so that we have, so like we did in the previous question, we're going to work with the left-hand side. So the left-hand side, what we have is k plus 1. What follows before k plus 1 is simply k, and give it a factorial. We are just working on the left-hand side. Then we want to prove that the left-hand side, the right-hand side. Okay, so at this stage now is what we have. So what we say, this is the same as, so this is equals to, so the concept or the idea that we're going to employ here is that we're going to multiply the two. Just expand this time, this, that. So k times k factorial, going to be k multiplied by k factorial. K factorial times 1 simply gets k factorial. So just expand. So after expanding now, after we do our expansion, we go back to the assumption. In the assumption, we're told that k factorial is greater than 2 to the k. So since k factorial is greater than 2 to the k, it means that this whole expression that we've written here is greater than, where there's k factorial, we're going to replace with, so we have k multiplied by 2 to the k, it's 2 to the k, plus 2 to the k. Why have we done this? Because this inequality and this inequality are the same, in the sense, or they're similar rather, in the sense that we are saying that k factorial is greater than 2 to the k, meaning that since it's greater than 2 to the k, then you can just replace this 2 to the k, knowing that this k factorial is greater than 2 to the k. Okay, so now from there, we're going to simplify it even further now. So the idea that we're going to use now is what we found just now. We're going to say this whole expression is greater or equal to. So the idea I want to bring in now is this one here. We know that k is greater or equal to 4. Meaning that where there's k, we can put 4 multiplied by 2 to the k plus 2 to the k, like this. So 4 is greater or equal to, sorry, k is greater or equal to 4, meaning that whatever expression we have, this k is always greater or equal to 4. So we can do that expression. So we are now at this stage, which is 4 multiplied by 2 to the k plus 2 to the k. Now we have a 4. But what we want to do is to make it look like the other side. What we're going to do is we know that 4 can be is better than 1. So this whole expression, what we're just going to say here where there's 4, just going to put a 1. Say multiplied by 2 to the k plus 2 to the k. And this is true. This expression which has 4 is greater than this expression which has 1. But why are we doing this? We're doing this because what we have on the left-hand side is just 2 to the k plus 1 to come out when we produce this. So now, what we have here is equals to the one we just multiply with this, give us 2 to the k plus 2 to the k. So now, it's just a matter of adding these two. So adding these two, we're just going to get 2. So this is as good as algebra when you have a plus a, because it's just 2a. So since we're adding this and the like terms, so we're going to get 2 of these. 2k. Then this will be the same as 2k multiplied by 1 for 1 there. Then this will be the same as 2k plus 1. Now, this gives us our right hand side. So now, this is greater than this, it's greater than that, it's greater than that, it's greater than that, everything is equal to this, meaning that the left hand side is greater than the right hand side. So this proves that this is greater than that expression that we have. Okay, so I think for this video, just do these two examples. I hope you're able to follow it.